Okay, here in example 6 from the chapter on Laplace transforms, we're given yet another transform variable y of s. We've taken our equations of motion of the system, Laplace transformed them, and got the output variable there of y, the transform form of that, and that's what we end up with. So we've already done this work. And what we want to do is find out what the response y of t is that corresponds to that. The denominator here of y, we know that's coming from the dynamics of the system. That's really sort of the left-hand side of our input-output equation. Being that's in the denominator, we'll call it d. The top part, we're not sure from where it came. We'd have to know more about the details of the original input and output model. The 5s squared plus 3s plus 7 could come from initial conditions, it could come from inputs, or it could come from combinations of those. At this point, we really don't care. All we want to do is just find y of t. So we know that the first critical step here is to first find the roots of the denominator d. These are called the poles. It's a cubic function in S. And I think to get these roots of minus 6, minus 4, and minus 2, I probably use the roots command on MATLAB, and that's what we get. Again, a minus 6, minus 4, minus 2, and the key notes here is that we have distinct, no repeated roots, and they're all real. So that helps guide us to what we expect here for the response. So we know that y of s, given above, I won't repeat that here, it's right above there. Our goal here is to write this in terms of its partial fraction expansion. A1 over s plus p1, a2 divided by s minus p2, and a3 divided by s plus p3, sorry. So that's going to be our goal whenever we have distinct roots. Okay, so that's key. And then we look back to our nice formulas that we have for extracting these residues here of A1, A2, and A3. It basically says that we take the transform variable s, y of s, we multiply by s minus the first pole, p1, y of s. And from that, we substitute in s equal to p1, which is, looks like from here, is a minus 6. So let me repeat this here. I get s minus p1 times 5s squared plus 3s plus 7 divided by, what do we have here? S minus p1, s minus p2, s minus p3. Now before we do the evaluation here of s equal to minus 6, we need to first recognize that by multiplying through by here, we need to cancel out this first. Otherwise, it's going to be hard to figure out what this is. So we cancel that out first. Then we set in s equal to a minus 6. So this is 5 minus 6 squared plus 3 times minus 6 plus 7 divided by s, which is minus 6, minus p2, well p2 is a minus 4, so that's a plus 4. S evaluated is a minus 6, minus p3, which is minus a minus 2, so that's a plus 2. So in the end we get 169 divided by 6. So that's too hard to do. We repeat the same process here for A2. A2 is S minus P2 times y of S. We evaluate that a product at S equal to the second pole, which the second pole we see here is a minus 4. Again, I'm going to multiply S minus P2. The numerator is 5s squared plus 3s plus 7 divided by S minus P1, the factored form, S minus P2, S minus P3. Evaluate that result in the end at S equal to minus 4. Again, we strike out the S minus P2 first before we do our evaluation. That becomes S is minus 4, so that's minus 4 squared times 5 plus 3 times minus 6. Oops. Wrong line there, isn't it? So that's a S equal to minus 4 plus 7. And S here is a minus 4. Minus a minus 6 gives us a plus 6. Minus 4 minus a minus 2, so that's a plus 2. In result, that residue from that method that we have here, it ends up being a minus 75 over 4. So that's our A2. Repeat the same process again for A3. This is S minus P3 times y of S, and y of S again is 5s squared plus 3s plus a 7 divided by our factored form here, S minus P1, S minus P2, S minus P3. We're very careful here before we evaluate S here equal to P3. And P3, let's write that down again. P3 is a minus 2. That before we do that, we strike out this. We cancel out top and bottom of that. And we get 5 times minus 2 squared, 3 times minus 2 plus 7, and we get S, which is minus 2. We get a P1. I need to scroll back up here to see what that was. That ends up being a plus 6. You get a minus 2 plus a term here of 4 as that. This evaluation gives us 21 divided by 8. So the process that we went through to extract our residues there of A1, A2, and A3, we can say that y of t then is the inverse Laplace transform of A1 divided by S minus P1, A2 divided by S minus P2, plus A3 divided by S minus P3. And the step here, which is important, is to recall that the inverse transform of S minus P1, P1 was a 0. So basically the inverse Laplace transform of 1 over S is a step function. So that would be h of t. We have an A2, which is multiplied by the inverse transform of S minus P2. So that's equal to e to the minus 4t plus A3, inverse transform of the last term, which is e to the minus 2t. For A1, we found that that was 169 over 6 h of t. plus A2. A2 was a negative sign, so let me change that minus plus to a minus, so that's 75 over 4 e to the minus 4t, and A3 was 21 over 8 e minus 2t. So this, without even knowing from what system our Laplace transform variable y came from, this is the response. We don't know really what the excitation was, what the initial conditions are. We don't really care, because once we have y, we just simply need to do the partial fraction expansion. That really translates into finding the numerical values for our residues there of A1, A2, and A3, with the very important step here of first knowing the inverse Laplace of 1 over s is the step function. Laplace transform of 1 over s minus p2 and 1 over s minus p3 are the exponentials. Important things to remember.